Everyone. Hope you are enjoying your dialogue. Welcome to this tutorial. I am Pooja Dash. I'm a postdoc at the SDS lab working with Professor Aurav Ganguly. I was actually a PhD student of him and I was a PA or program assistant for one of his dialogues in 2023, which happened in India and Nepal. So I'm pretty familiar with the course content and what you are learning about and everything. So in today's tutorial, we are going to learn about the art system models and a brief overview of what they are, where we can find them, how to download them, or how to visualize them and work with them. So I hope you enjoy the tutorial. After this, we are going to have a live Q&A session where if you have any questions, you can ask me and we can go through them together. Also, if you have a problem following the tutorial, let me know in the Q&A session and we can address those in that session. So let me start by sharing a PowerPoint presentation about um, art system models. We are going to look at overview of art system modeling. And so what is art system science? So it's a our system science represents our approach to which studies our planet. So rather than examining atmosphere, oceans, land, and ice in isolation, we recognize that Earth functions as an integrated system with complex interactions between its components. So this holistic perspective is absolutely essential for tackling the climate change challenges we face today. So, what are the key components here? So, first, what in the earth system science, as we talked about, the key components would be atmosphere, hydrosphere, cryosphere, biosphere, and geosphere of all the gases that surrounds our earth. The hydrosphere means oceans, lake, rivers, and groundwater. The cryosphere is the frozen water in ice sheets, glaciers, and sea ice. And biosphere is all living organisms. And lastly, the geosphere is the solid earth from crust to core. So each component operates according to its own principle, but they are all connected through exchange of energy, matter, and momentum. So next we have feedback mechanisms. So these are crucial for understanding climate change. Positive feedback amplifies an initial change, and negative feedbacks on the other hand, it dampen the change. We have to incorporate these feedback mechanisms inside the art system model so that everything is the relationship between everything is nicely put there. The third concept is system dynamics, and so art doesn't always respond linearly to changes. So small perturbation can trigger dramatic shifts when thresholds are crossed. We can call this tipping points and everything. So I'm putting out a lot of new concepts, I know, but if you're interested in any of them, we can discuss further. But let's just give a small description now. And then there are time scales ranging from weather to paleoclimate. So weather means days, the weather changes day to day, and paleoclimate can be millions of years. Why observation data are needed? Because before developing these complex models, scientists need observational data to understand Earth system processes and validate the model outputs. So Earth observations come from diverse sources, it creates a foundation for model development and evaluation. So, type of observation could be in situ measurements such as weather station, ocean buoys, radio sondes, aircraft measurements, and then there are remote sensing data sets such as satellite-based observations of atmosphere, land, ocean, and ice. We obviously have radars and lidars, which give us information about precipitation, clouds, aerosols, and land surface measurements. Next, we have reanalysis dataset. So, reanalysis actually combines observations with numerical models to create a comprehensive datasets of the Earth systems. So, these products provide graded, physically consistent data for climate studies. So, we can also call this the best guess of historical climate condition. So, it is created by combining observations with numerical model, as I said. You can think of them as a reconstruction of Earth's climate history on a regular grid. So the advantages of this could be they provide complete coverage in space and time because in observations we sometimes have missing data, and they do not have any gaps in the records, and they maintain physical consistency. They avoid like conservational loss, and they integrate diverse data sources such as from the satellites, weather balloons, ship reports they combine everything into a coherent framework. And also they include uncertainty estimates helping us understand their reliability. But they also have some limitations, such as model biases, the influence, like model biases influence results, especially for variables that are like not as nicely constrained by observations. The changing density of the observational network introduces artificial trends, particularly evident before the satellite era. And some of the examples would be for the atmospheric data, we have ERA5 from ECMWF, from which is a European Union data. And also we have dataset from ocean, land surface, etc. Next, again, our system models, they are comprehensive numerical representation of the physical, chemical, and biological process governing the Earth's climate system. They have evolved from the simple, like they were called general circulation model, to incorporate more components and interactions. So the components now are atmosphere, ocean, land, cryosphere, and biogeochemical cycles. Now they have different resolutions, 100 kilometer in the Earth system models, but sometimes they could go even further, like 25 kilometer grid cells. So what are resolution? Resolutions means for each grid cell, we will get one data for that area. So think of a square box of 1 kilometer by 1 kilometer maybe, and for that 1 kilometer by 1 kilometer box, what is the temperature, or what is the precipitation? So that is the spatial resolution of that data set. And then there are process representations. So our system models, new physical and biogeochemical processes are being added, and they try to solve these interactive connections between all the components. And also there are a lot of complexity you can think of, because not everything can be put into equations, what happens around our earth, and such as the dynamic vegetations, ice sheets, atmospheric chemistry. So these are some of the complexity, and I think one of the major ones is the cloud physics. Now, what is CMIP? So, CMIP actually coordinates this climate model experiments that involve multiple international modeling teams to better understand past, present, and future climate. And CMIP6 is the sixth phase of the project and the latest one. We are soon going to have CMIP7. And so it's a CMIP is a project of the World Climate Research Program, working group of coupled modeling, or WGCM. So the key questions they try to solve is, how does the Earth system respond to forcing? Means how the Earth reacts to different amount of carbon dioxide, and we get this radiative forcing, or amount of warming of the Earth due to different amount of carbon dioxide in the atmosphere. And then what are the origins and consequences of systematic model biases, and how can we assess future climate changes given climate variability, predictability, and uncertainty in scenarios. So there are different experiments that are solved, such as this diagnostic evaluation and characterization of climate, and then historical simulation from 1850 to present. Scenario MIP does the future experiment of projections using shared socio-economic pathways, which I am going to explain later. And so all in all, there are 21 CMIP6 endorsed MIPs. So these MIPs are the parameterizations, that is specialized experiments for specific research questions. So these are some of them, such as we have for clouds, we have CFMIP, so that is Cloud Feedback Model Intercomparison Project. Then we have GMMIP, which is for Global Monsoon Mission, and LUMIP, which is for land use, and all of that is given here. Now, models are increasing in complexity and resolution. Earlier, we had only global circulation models. Now we have Earth system models that has biogeochemical cycles. So we have improved the physical processes, and also um, we have improved from GCMs to ESMs now. We have improved our resolutions. Earlier we had, suppose something was 130-kilometer resolution orography, and you can see these boxes which holds the data. And now if we have a 25-kilometer resolution, we can see these peaks of mountains, or this is maybe a land data. So peaks of mountains and the elevations there more clearly. And this is allowing us to study the processes as a horizontal resolution increase to weather resolving global model resolutions. Top one is showing how the interactive processes are being modeled, and the bottom one is actually showing what is the growth of climate modeling. So in the 60s we had only some amount of processes being modeled, but now we have so many processes are being modeled. Now coming to the scenario model intercomparison that I talked about, or scenario MIP for CMIP6, and shared socioeconomic pathways. So what they do, they try to figure out what would be the future projection scenarios. So how much warming will we get? So you can see this 2100 forcing level in watt per meter square. So if the world is greener and there is not much carbon dioxide in the atmosphere, and no new emissions are being released, everything is green, then we can consider less warming, or less amount of radiative forcing, which is 2 watt per meter square or 3 watt per meter square. But if there are a lot of carbon dioxide in the atmosphere, then it increases the temperature overall, and then we would have a higher forcing level, so it can go up to 8.5 watt per meter square. Now what they have done, they have divided this warming level into 5 SSPs: 1, 2, 3, 4, and 5. They have also incorporated economic or socio-economic data set into these forcing data, forcing levels. So what they do, if there is a certain warming level, or if there is a certain forcing level, then how much the society is going to be impact, what would be the economic condition, how much would be the population. So they have considered all of this, and then they have come up with the SSP. So that's why they are called socioeconomic pathways. So SSP1 is sustainability, which is very good, and then we have a very low forcing level such as 2.6. So there is a famous one like SSP 126. So what this 126 means, the first letter or first number 1 is actually the like SSP's name or number, and the second 26, these are known as the warming level or forcing level. So 2.6 would be the warming level. The next we have one is called SSP 585. You would see this in the next slide. So 5 means the fossil fuel development. So we would use fossil fuel everywhere, and that would emit a lot of carbon dioxide. And 85 means 8.5 of warming or forcing level. Next we have SSP2, which is known as middle of the road, SSP3 as regional rivalry, SSP4 as inequality. So this figure might be a better one to show. So here we can see that how much temperature will rise according to each scenario. So as I told you about, there are 5 SSPs. So here we are seeing at 4 now. So SSP 126, 245, 370, and 585, and one data is historical. So you can see that from 1980 till 2000 or 2014, we have the historical data set. So till that we have one line, and then there could be multiple different future scenarios. So in the SSP 585, the warming increases up to 8.5. Now, what is the corresponding changes in temperature? So you can see if there is SSP 126, the green ones, the temperature, or this is the temperature in Kelvin scale. So it doesn't change from the baseline too much. So the baseline is taken from 1995 to 2014. So it almost stays within 1.5 to 2 Kelvin change. But if it goes to 8.5, we can see that the temperature change, or change in temperature, can go up to 6 Kelvin to 7 Kelvin. So this is a change. So it is similar to degree Celsius also. So 6 to 7 degrees Celsius change can be seen if the future scenario follows the SSP 585 trajectory. So these are important to look at the future projections, because in future we do not know what is going to happen. That's why we do not call them predictions or anything. We call them projections. We try to see what if scenarios and what will happen if this much amount of warming is in the atmosphere and this much amount of carbon dioxide in the atmosphere. What will happen to the changes? What will happen to the temperature? So now these experiments are run by different organizations around the world. I have given some of them and where they are from. So one, you can see in USA we have multiple models such as CESM2, which is from NCAR. MCM is actually from University of Arizona. E3SM one is from Department of Energy, DOE. GFDL is from NOAA, and GISS is from NASA. So, and there are others also, but I have listed some of them. So from France we have CNRM and IPSL. From UK we have, from Korea, China, Canada. So from all the countries, not all the countries, from some of the countries, we have a lot of these climate models. I would say the number is ranging between 45 to 50 different institutions. Now, there are different techniques for climate model or climate data analysis. So, we can do bias correction because these models might not be giving us the correct results, and we can evaluate them, and then we can do bias correction. Then we can do multi-model ensemble analysis. As we saw, we had 42 different type of modeling groups, and we can take an ensemble mean or median from these different groups. So each group's output can be one ensemble, and then we can take the mean or median to do some analysis. And then we can do statistical downscaling, so which increases the resolution of model outputs. So if we have something at 100-kilometer resolution, we can drill it down to 25 kilometers so that it's better, and I mean, more physical processes are generating into each grid cells. We can do extreme value analysis to analyze the rare events and their statistics, and we can also do pattern scaling, relating regional changes to global mean temperature and all of that. Now, what are some common data formats? So, which is a very good format, I would say, as I have been working with a lot of format. So this is self-describing and they are machine independent data format. Then we have GRIP format or HDF5. You can have like weather or climate data in these formats. Basically, they are rasters. So they are divided into latitude and longitudinal grids, and in each grid they would have a data, and how this data array is processed or stored, that's what we are talking about. So mostly they are stored in netcdf format now. And what are the tools? We can use programming language such as Python or MATLAB. Some of the, I think the very important library for working in Python in the climate science field would be Xarray. So it handles the data sets very easily, and we can plot them. We can get the data set statistics very easily with using Xarray. So if you are new to coding, or if you want to learn this climate science modeling or how to visualize them or data analytics, please learn Xarray. And then we have CDO, NCO, Cartopy, and all of that. We have some softwares also that help us visualize the data sets without using coding, such as Panoply is one. I have used that. It is very user friendly, so you can use that one to visualize some of the data sets. Next, I am going to talk a little bit about extreme value analysis in climate science, because we are doing one experiment with that concept. So I'm just going to give a brief climate extremes, whether they are floods, droughts, or heat waves. They often cause the most significant societal impacts, as we know. And these events reside in the tails of a probability distribution, making them challenging to characterize with standard statistical methods, because this doesn't happen every day, and we also have very less amount of data. So this is where extreme value theory becomes invaluable. So the foundation of this approach is generalized extreme value distribution. They they unify three classical distributions such as Gumbel, Fréchet, and Weibull into a single mathematical framework, and each of these addresses different type of extreme behavior. So the GV distribution is characterized by three key parameters, that is location, shape, and scale. The location parameter, it shifts the distribution, like which is the distribution left or right, and the scale parameter controls the spread of the distribution, and the shape parameter determines the behavior of the distribution's tail, like how the tail is. In practice, we typically apply two main methods to fit this distribution. One is block maxima. So we consider a block that can be a year, and within the year, what is the maximum value? We took those value to get these extreme value distributions, or peak over threshold approaches, which is we consider threshold, suppose 95%. So any data we have above 95%, those will be our extreme data sets. What we can use this analysis for? So we can do the return period analysis, which is how often on average we expect events of a certain magnitude to occur. So if we have a 30-year or 100-year return period levels, so we will see this in our Python code. So this concept forms the basis of infrastructure design standard worldwide. So if we want to design a structure for 100 year, then that we need to find out what is the 100-year return period event that the structure needs to withheld against. So if we are building a sea wall, and then we would like to know what is the sea level rise, 100-year sea level rise, so that that structure can stand out till 100. One misconception is that if we say an event is 100-year, you might think, okay, it happens every 100 year. It's actually not like that. It's the probability of happening that event. So what we consider is, if an event has a 100-year return period, then the probability of that event happening in any given year is 1 over 100, or we can say 0.01 or 1%. So next year also it can happen, but the probability of that happening is 1%. So that's how we calculate. If the these are very important concepts for risk assessments to inform infrastructure design and adaptation. And also we will like to see how the extremes would change over time. So if an event is 30-year event versus an event is 100-year event, that would be more extreme, and we would like to see how much we need to be prepared for. So engineers, urban planners, policymakers, they all rely on this analysis to prepare communities for changing climate. So I hope that gave you a brief description about extreme value distribution analysis. So we'll work with some precipitation data. Okay. So I will share all of these like this PowerPoint with you. And next, let's go towards how to download the data sets, where we will find them, and then we will do a small experiment in Google Colab, and we will do some Python coding, where I have given you some codes which you can tweak and then get different results and everything. So let's go towards that. So let's look at this website, which we have for CMIP6 results. So this is the home page where we can get all the CMIP smart system model outputs from the CMIP6 generation. This link I will also give to your PA, and she would share them with you. Now, this is the home page, and you can see how much data we have. We have, okay, is that 14 million? I think it's 14 million data set, or more than 14 million data sets almost. So many variables I would show you, and then so many modeling institutes and everything. First, let us go into CMIP6 data info so that we can, so I just clicked on this, and there is a brief descriptions about the MIPS or the different parameterizations they use, where the dataset is hosted. So one is this in USA, or Lawrence Livermore National Laboratory in California. So I think I was in that, or yes, I am in that website hosted by USA. But other countries also host these datasets, such as in Germany, France, UK. We can have these datasets from there also. And then you can see the modeling groups and their contributions. So inside United States, as I told you, different national labs and different universities also produces the data sets, such as University of Arizona. We got the Argonne National Laboratory, and Lawrence Livermore National Laboratory, and all of that. So you can check out this website. This is a nice one to get a summary of everything. And then there is a summary table of currently available data for different modeling institutes, and then these are different experiments that they run and everything. Okay, so you can look at all of that. Now let us see how we can download a data. So today we are working with two very basic variables and very important variables. So one is temperature and another one is precipitation. So temperature is a state variable, and we can fairly say that CMIP6 models are quite good in terms of getting the equations right for analyzing temperature or projecting temperature. So one is that, and another one is precipitation, which is a very complex variable, I would say, and usually it is very hard to do the experiments or how to run the equations to get the precipitation. The biggest challenge would be, I would say, cloud physics. We are not very good at getting the cloud physics right yet, so that's why we have a lot of uncertainties in the approximation of precipitation in these results. So let's work with those two. So how to get those? So if you look into classification and if you click this arrow, so first we will select the variable ID, and you would say these are some letters which doesn't make any sense, but if you know the short form of the variables that we are trying to look for, then you can go directly from here. But since we are doing, so we can select the temperature data here. So on the top we can see air temperature. We can select that one, and the variable ID would be TAS for that one. So this is temperature of atmosphere or air measured at the surface. So we can select this variable. So now you learn that the variable that we should look for temperature is TAS. Next, we have to look for the frequency, which is, it can be hourly, 3 hourly, 6 hourly, daily, monthly, all of that. And we have sub hourly data set also. Now let's look at the daily data set for our today's experiments, because we are going to work with some extremes. So it's going to be necessary for us to look at the daily data so that we do not lose the extremes while averaging the data set for a month or a year. So that's why we are taking the daily data set. So next we are selecting daily. So each time you select, just do a click outside so that it narrows down the search and everything. So first we selected air temperature or TAS. You can directly select TAS also, now that you know the name of the variable, and then frequency, which is daily. Next, we will go to the identifiers and we will look into some of this. So in the identifiers, you would see experiment ID, source type, institution ID, source ID. So you would look into two of these. One is experiment ID and source ID. Now, what is experiment ID? We have different kind of experiment to find out what is the carbon or carbon dioxide situation in going to happen in the future. So the first one, you can see 1% carbon dioxide. So that means if the carbon dioxide increases 1%, what would happen and everything, right? Now we would also like to see, so see, there are other things like abrupt P5 times of carbon dioxide, or abrupt 2% of carbon dioxide. So if there is a abrupt change in carbon dioxide, and it becomes double, then what will happen? So all of these experiments are there. But you'd like to see, first of all, historical data set. So I am just typing historical. So you would see there is historical, and then we would also like to work with another SSP. So which would be SSP 585. So you'd look into the highest amount of warming for the atmosphere and see how the temperature and precipitation data set would look like for that. Next, the source ID. So these are different kind of models that are available for temperature data set. Now we can select the institution also, or we can select the source ID. Now I am selecting a source ID called CAN ESM5. So this is a Canadian model. We could have selected any of the files, but I would tell you why I have selected that later. Now we have CAN ESM5, historical, day, and temperature, right? Now we are ready to download. So we can see all of these files. So all the only thing that is different between all of this is this number R19I1P2F1 or R18I1P2F1 R24I1P1F1. So these are different initial conditions. So if you know, these experiments are run multiple times by changing the initial condition very slightly. So for each time, if we change the initial conditions of these equations, then the output becomes quite different. So that's why they need to run multiple scenarios or multiple of the simulations by changing the initial conditions very slightly. For our experiment, we do not like care how much the initial conditions and what the initial condition is. We can select any of them. So you select this arrow, and then you would see the data set, and this is the download link for you. But do not download this one if you are not familiar with working with wget. So you can download this file with the wget files also. This would give you that file, but I would say just download from here or using this link. So if I click this download link, um, you would see that it might start downloading. So it started the downloading. Yeah, it started a bit late, but it started. So you can see the my file is getting downloaded here. So I'll not now. Why I chose this CAN ESM5? One of the reasons for that is ease of working here. So see, for each file there is just I mean for each model there is just one file, right? It shows the number of files. Now let us select a different model. So instead of CAN ESM5, we could select USA one, American one. So CESM2, it's from NCAR. So I selected that. So again, we have 54 dataset, just changes, the changes in this number for different initial conditions. Now what do we see? We have 17 different files. If we click on that, we can see the different files that we have. So what are the changes here? So the historical, one thing I forgot to tell you, the historical data set is from 1850 to 2014. So these are the time period for the historical experiment, and the future ones start from 2015 to 2100, or some are even till 2300 as well. So this 1850 to 2014, some of the models they divide this time frame into smaller time frames, and for each time they give a data. So see this one, the first one is 1850. So how do you read the file? I'll show you that. But first let's look at the time first. So 1850, that is the year, and then 01 is the month, and 01 is the date or day, and then 1859, 12 is the month, and 31 is the day. So December 31, 1859, it stops, and then again from 1860 it starts again and goes till 1869. For every 10 years they have provided a data. That's why we have 17 files. So 17 into 10 is 170 files and all of that, right? So you have to download each file separately and then work with them and maybe merge them together and then work. So it's a bit cumbersome. If you are interested in working with these files, let me know. I can provide you a code to merge these files. But for now, let us just look into the CAN ESM5 one, okay? So let's go back again to CAN ESM5 and let's see what we have. So now I would show you how to read these files, okay? So you already know how to read the date. So 1850 January 1 to 2014 December 31. So this is the time frame that we are looking for historical period. And then the first thing is the variable name. So that is TAS, TAS for our temperature. And then DA, that is for daily frequency. Next, we have the model name, that CAN ESM5. Then we have the experiment ID, historic. And next we have a variant level, or this is the type of initial condition. And GN or GR sometimes is used for if it incorporates land or atmospheric variable and all of that, right? And 1850 to 2014. So for the atmospheric variable, it's usually GN, and this is how you read a file. So we are done with downloading the task file. Next, download another file from SSP585. So we search with SSP585 and we get this one. So just select this one with no other things. And if you select this one, we get this file. Oh, it started downloading. Nice. Okay. So if you can download it from here. So if we click on this thing, it will download it from here. Now I would say pause the video and download the file for precipitation by yourself. But and see if you can do that, right? So just I would go back to the home page and pause the video and download a precipitation file, any precipitation file for experiment of historical experiment and historical, and the variable name here is PR, only P and R. So I would look into this classification. The variable ID is PR, so I'm searching PR. So yeah, if I look into just PR, where is PR? So this one. So if I have the variable PR, then this is the precipitation, right? So pause the video and download the precipitation file by yourself. But I will continue to show you the process so that you are already done. You can match if you could do it. Okay. So next we would select the frequency, which would be daily for us, and then we'll go to the identifier. Experiment ID would be historical, so this is historical. And then institution ID, again oh, not institution ID, source ID, so that would be CAN ESM5. So I'm going down and this is CAN ESM5. Again we have 221 files. So how to download? You click on this arrow, you get this link, and if you click on that, the file will start downloading. So this is the file getting downloaded. So I hope now you know how to download the file. If you do not know the name of the variable, which is very common initially, so you click on the CF standard name. So I'll unselect the precipitation, and then you can select the all of the variables that is here that you want to work with. You can work with relative humidity. You can work with runoff, hydrologic variables, and atmospheric variables, and all of that. Then you can choose different climate models, from different institutions, and then experiment IDs and everything, right? So this is how you download. But one thing I would like to say, the files are quite large because we have selected a daily data. So the file would be in the range of at least 700 megabytes to 1 to 2 gigabytes. So you should have a good internet connection if you want to work faster. Otherwise it will take a lot of time to just download these files. And yeah, and you should have enough space where you want to work on, and that's how you can work. The tutorial, I have already given the link of the files that we are going to work with, and you can download directly into the tutorial. And we'll go on to the tutorial now. But I hope you have followed the instructions so far nicely, and you are ready to work with the climate dataset now. Now let's look into how to work with Python. We will use Python today to visualize these Earth system models for historical and future projections, right? So today we will use Google Colab. So it's a platform which lets you write codes and then visualize your data sets and also save the figures and everything without installing any other I would say environment or Jupyter notebook and anything. So you can just use Google Colab, which lets you code, and then you can it has different cells which you can run, and then you can have your own code. So if you do not have any coding experience, do not worry, because the code is already there, and you do not have to write one by yourself. But not share my screen. So you open a tab or you open the Google Chrome, and then you search Google Colab. If you do that, the first link you get, welcome to Colab Google, click on that, and then you might not have any of these files that I have, because if you have started for the first time, this might be empty. So in this case, you will upload the file that I'm going to give you, right? So if you click on upload and then browse, it will show you the IPYNB files you have. So I'm selecting this tutorial ESM and then uploading here. So now we have this. So this is how the interface of Google Colab looks like. So we can use either this code or text cell. So if you add a text cell, it would let you write a text, such as we use this for some comments, or sometimes we use this to explain what we are trying to do here. So we can, like, I can write welcome DOC students. If you click outside, it would be done, right? So what we are doing, we have first we will download the dataset for precipitation and temperature. As I told you, historical dataset is from 1850 to 2014, and future we are using SSP585, which is the dataset from 2015 to 2100. So this is the code that if you run, it will download the files for you, and it would save here in this files section. So at the left, you could see this file, or like file icon. If you click on that, currently I don't have any data, but if you click on that, it would be saved here. Now, mind you, once you use this code, this is just good for the coding session once. So if you download it, it would be saved here. But once you close your laptop, or once you close this window, this downloaded files will be gone from your Google Drive. um, Another good thing to remember is, please have enough space. I mean, you usually have a good space in the Google Colab. So see, I have 70.81 gigabyte available. So I am downloading only 4 files, so I'm good to go here to download my files. But you can also download, as I showed earlier, how to download them and save them in your Google Drive, and then mount your Google Drive with Google Colab. I mean, make a connection between Google Drive and Google Colab, and from there also you can call your files from in which folder you have saved it, right? So today you do not have to download it completely. I know you are in a classroom, and the internet might not be that good, and I do not want you to download it twice. So just click on this one, and it will start downloading for you. So it will take some time to download. So I will just let it download, and I mean, I'll come back after it gets downloaded, but I would say at least 10 to 15 minutes it might take to download all these 4 files. You saw that it took 1 minute 50 seconds to download one of my files. The first one did not download. I don't know why. I will check back again what happened there. But yeah, let's see. Let's wait for the others to get downloaded. Two of my files got downloaded. The third one is getting downloaded. So how do you know that your file is downloaded and it is good and nothing bad happened? So see these status bars, like 100% is downloaded. The file size is 886 megabyte or 792.2 megabyte. And it took 29 second. The first one took 1 minute 50 second. The last one, its ETA is saying 1 minute 52 second for now, but let's see how much it gets downloaded in time. But I think this will get downloaded. But the one at the top, the first one, I don't think it got downloaded, because it says that HTTP request sent, awaiting response, but the bad gateway thing is there, so that's why it did not get downloaded. So the first one was, so if I think you know how to read the file names now. So we have 3 files. The last one is getting downloaded. The first one is PR day and SSP585. So it is, we can say, PR in future, precipitation in future. Then temperature in historical and temperature in future, right? So I think the one that we missed is historical and precipitation. So precipitation historical is missing. So I'll try to do something. Let's see if it works. Sometimes it's just that the website that it is pulling the data from is not responsive, and it shows a 502 bad gateway, but sometimes it works. So I'll just do that. You could also get any other file if you upload them and then save them in your Google Drive. You can also mount that file from that. I would show you that thing now. So you run this line of code. So currently these are commented out. So if you remove this hashtag or hash sign from the beginning, then it becomes a code instead of a comment. So you remove these, and if you line this line of code, and you show the location where you have saved in your drive. So you have to write the location. So for my case, it might be in content drive, my drive, tutorial doc, and then the name of the file that I want to work with. That's how we can call the file. So I think that would be the thing to do if you have it downloaded in your drive, and then you can call it from there. But I didn't want to do that because you have to download it first. You have to upload it in the Google Drive and then connect. But in this way, we are directly working with the, I mean, we're directly downloading the file in the Google Colab and working with that. One drawback would be is that once you are done working with that, it's gone, and then you cannot work with it again. You have to download them again next time you want to work with that. So the long term solution would be download it, upload it in your Google Drive, and work with that. But for this class, we are downloading it directly to save our time. Okay. So we are almost there. I think this one is 77% done. We have 1 more minute left to get it downloaded. Finally downloaded. So it says that it is saved, the whole file. Now the problem is our first file did not get downloaded, right? If I run this code again, all this file will be downloading again. Will be so I do not want that. So I'll make these as a comment. So I'll add a hash sign before them so that this three doesn't get run again, and these act as a comment, and the first one just gets downloaded. So let's see if it works now or not. Yeah, it works now. I don't know why it happens. So every time, it's just when I run all of this code, the first time it doesn't get connected and it doesn't download, but the next time it downloads. I don't know why it happens, how it happens. It's a very big file of 1.7 gigabyte. So it shows that it is going to take another 7 minutes for us. So let it download, and I'll be back after it gets downloaded. And also you can see the first file is now here, precipitation historical file. Okay, we have last 10 seconds left. It was a very long 6 minutes, but yes, let's see, we are almost there. So once it gets downloaded, we can start our coding part. You can see your files are getting saved here, and it is downloaded. So now we have all four of the files. Once you have that, I think our major hurdle is gone and we can start working. The rest will not be a problem, but I think you might have some problem in this section, like how to get the files downloaded, and if it doesn't work, like how to work around through it. But yes, I would say just try. If not, we can always talk at the Q&A session, like how to solve this problem. And this I showed you earlier, that you can use the drive mount thing. Next, let's go to the coding. So here we are using some libraries that would help us to do the analysis, right? But all the libraries are not usually installed within the Google Colab systems, specifically the ones that are not usually regularly used, such as L moments 3 and CF time. So CF times helps us with the with decoding the time coordinate inside the files, and then L moments 3, this would be used for extreme value distribution, which we will need later on. So just run this code, and it will install these two libraries for us. Yep, so it would write something like successfully installed this and successfully installed CF time. Next, we import the libraries that we need. So we need xarray, and we give a small name so that we do not have to write the xarray again and again. And then numpy, this is for numbers, np, then pandas, this is for tables and such. So we did pd. Then for plotting, we use matplotlib.pyplot, and it's a big name, so we give a short name as plt, and then L moments 3 and all of that, right? So we are running this code. It ran. Then we have the files, right? So first we will work with precipitation dataset. So we are going to get the files from here. So I am giving it name of historical precipitation file. The name I can get it from here. So if you just click on here and then rename file, you will get the name, and then you just command C to get the, I mean to copy the file name, and then you paste it here. And then future PR file is this one. The location now. So in this experiment, we will work at different locations. So I have put Santiago and Boston here. So you can choose any other city in the world. You just need to know the latitude and longitude of those locations. You can do a Google search. So if you just do a latitude of maybe New York City, right? And then it would give you latitude and longitude of the New York City, or the coordinates of New York City. So here I will be working with the coordinates of the locations you are going to visit. So you have started from Boston, because you are from Northeastern University, and then you will be going to Santiago, Punta Arenas, Cordoba, and so on, right? So I think you are in Santiago now, but yeah, let's see. So I am choosing Santiago and Boston for my first two locations, but we can change because we have the latitude and longitude of other locations as well here. And so we are running this code, it's run, and then we are opening this file. So DS means dataset, but you can give any name you want. Historical of precipitation, and we are using xarray. So we are using xr dot open dataset and then historical PR file. We are also opening the future file. So I'm giving a short name, DS historical precipitation, DS future precipitation, and also let's print the future precipitation just to see what it is. And I am using these two line of code just to fix the time dimension here. So you do not have to worry, just run this code. Yeah, this might take some time to fetch the dataset and open the dataset, and then it will print the dataset for us. And we'll look into what these netcdf files hold. So see, this file is almost 1 GB, and it has a time dimension, a latitude dimension, and longitude dimension. So we have 64 latitudes and 128 longitudes. So what does that mean? From, the Earth is -90 to +90 in latitudes. So in this section, for this 180 degrees, it is divided into 64 sections. So each section is almost, I would say, 2.5 degrees. Also, you can check it from here. See, so latitude is 87.86 and then 85.1. So if you subtract one from other, you would see what is the grid size in the latitudinal scale. And then longitude, so we know that it is from +180 to -180. So again, we divided this 360 into 128 groups, so we have this much. So 0, and then 2.8, 5.625. So I would say it is roughly 2.8 degrees. One grid box is 2.8 degree by 2.8 degree. Now 1 degree is actually almost 110 kilometers. So we can say roughly it is 280 kilometers by 280 kilometers square box. So for each box, you would get a temperature or a precipitation value, right? Then we have what are the variables stored in here. We have time, latitude, longitude, and the name of the variable, that is PR for our case. Okay, sounds good. Next, we are doing some code to change the longitudinal values. See, the longitudes are actually 0 to 360. It's not -180 to +180. It's the whole 0 to 360. But usually when you search the coordinates, it gets into minus values instead of into 0 to 360 values. So that's why we are just changing the longitudinal values so that it changes it to -180 to +180 range. So I'm running this code and then printing one of the files to see if the value has changed. And see, now it has, instead of 0 to 360, it's 0 to +180, and then it goes back around and then -2.812 and then 0 again, right? Now these files, you can see these are not sorted nicely, so we'll just sort them according to the longitudinal values. This is that. Next, let us plot one of the files. So this is file, or this is the figure that will be creating for the precipitation. So I selected any date you want, and this is from future, so I have selected a future date, not so much future because now it's 2025. So let's change the date. Instead of 2023, let's do it 2028, and then run the code. So now we have in 2028, July 15, the precipitation files look like this. So here we can get some other informations also. So the longitudinal values is from now 0 to 180 here, 0 to minus 180 here. Latitudes are minus 90 to plus 90 here. And then the precipitation file has a, or variable has a unit of kg per meter square per second, which is not very commonly used. So we will change that. And that's why the values are so small here. So it's showing per second how much precipitation is going to be there, right? So that's why I am multiplying it with 86,400 to convert it from kg per meter square per second to millimeter per day. So if we run this code, it would change the units from kg per meter square per second to millimeter per day. Okay, let it run, and then we have some helper functions that we have used for the extreme value distribution theory, or to find out the return levels and everything, right? So we have generalized extreme value theory wrapper and fitting the distribution and giving us the return level and everything. So let us run this code also. So this is taking a bit of time because it is multiplying each precipitation value. We have so many values for so many years to 86,400. That's why it is taking a bit of time, but it will be done soon, and then this will be done. Next, we will come towards the location file, right? So we will select two location 1 and location 2. So let's select location 1 first. So our location 1 will be, maybe, I think we have already selected location 1. Yes, it is Santiago and Boston, so we do not have to do anything. So you already selected it here, and our file got run. Yes, so this is run, this is also run, and location 1 is already there as Santiago. So we can just start with this one. So what it is doing is calculating the annual maximum value for each location. So this location I'm selecting is Santiago. So it is taking the latitude and longitude of that. And from the grid files that we have, it is selecting the closest latitude and longitude in the netcdf file and finding out what is the annual maximum precipitation of that location for each year. Because this is the block maxima approach we are using to find the extreme value distribution theory. So it got ran, and let's just see how does it look like. So annual maximum future for location 1 and annual maximum historical in location 1. So I'm plotting the future one here. So these are the years, number of years that I have in future from 2015 to 2100. So around 85 years, and then these are the values in millimeter per day. I did not put any axis or anything. Let us do it here. So plt dot x label, we can do maybe number of years. It is not giving us the year values for now, but we can change that as well. But let's just do it here. PLTY level is precipitation, and we also write the unit millimeter per day. And what do you want? We want grid, so plt dot grids. And so yeah, let's see. Okay. And yeah, if we run it, we have the number of years in future and everything, right? Okay, now we are doing the same thing for location 2. Okay, think I have location 1. Yeah, this is location 1. Now we are doing it for location 2. We are again getting the annual maximum values for location 2, both for historical and future. Once it is done, we are going to calculate the return levels. So we are going to calculate it for 100 years. So calculating what is the return levels for return periods of 1 to 100. Next, this is a long code, but do not worry. This is just plotting them, plotting the values in a nicer way. So let's see if it gets run, then we will have our result. So see what it is saying. We have Santiago historical, Santiago future, and Boston datasets are plotted in a dashed line. So Boston historical and Boston in SSP 585. These values are in e to the power 2. That means just multiply 100 with them. So 1.8 means 180, 1.6 means 160. The written levels are in millimeter per day. These are written period in years. And now what it is saying, let us understand this one. So a 100-year return period value for Boston in future is 172.35, whereas now, like for historical data set, it is 112. So if you look into this value 112 and try to find it in the red line, so I'll think of a straight line here and it is crossing almost here, I would say, which is a not even 10 years return period. It is like an 8-year return period event, right? So what does that mean? Currently, the event that has a chance of happening every 8 years in future, currently the event that is happening every 100 year, or that has a chance of happening once in every 100 year in future, that event will happen in every 8 years or have a chance of happening in every 8 year. So I hope you can understand this. The precipitations are become more intensified, their frequency is increasing, their magnitude is increasing. Whereas for Santiago, I don't think the values actually differ that much. These are quite similar. So we can compare like different trends and everything. Another thing we can compare, like from 30-year return period to 100-year return period, how much it is changing. So that's why I have plotted this 30 and return period values also. So Boston 30-year return period values is 142 in future, and then 100-year is 172. If I divide this 100-year by 30-year, and we get a ratio of PEVI, that is precipitation extreme volatility index, and we can see how much the value would change from 30-year to 100-year return period. The higher the value is from 1, that means the greater the difference between 30-year and 100-year return period. So we would see the maximum is in Santiago future, I would say. So Santiago future is orange color. So in 30-year return period, it was I would say 52, but in 100-year, the change is maximum here. Although the number is not that great, but the ratio is very greater than 1, so that means it has a high change. So these are the things we need to consider when we are designing an infrastructure. If we want to make our infrastructure concrete, or think of this one. So maybe in 1980 someone was building a dam and they made it safe for 100 years, and they considered the value of precipitation of 112 millimeter per day. Just after 20 years or 30 years, before even 100 years, this value gets changed to this 112 millimeter per day, which was previously 100-year return period level. Now it becomes a 10-year return period level or 8-year return period level, and every 8 years this value is the dam is experiencing this high amount of precipitation. So will it withhold that much amount of water in future, or for how long? So this is why we need to consider the changes in the um, precipitation value due to climate change. Now, this is an extreme scenario because we have looked at SSP 585, which has the most amount of global warming or most amount of carbon dioxide in the atmosphere. But it still shows that it is necessary to look at all the scenarios, and not just the green ones or the middle of the road ones. We have to see and look at what might be the possibilities or what might be the projections for future precipitation. So this one was for precipitation. Now we will do another experiment with the temperature files. So similarly, this is the same code. So we are calling the historical temperature file, future temperature files. We are opening them with xarray, then solving the time issues, then getting the latitude and longitudinal values. We are changing the longitudinal values from 360 degree to -180 to +180. Then the values usually are in Kelvin scale. We are changing it to degree Celsius. So that's why we are subtracting -273.15 to change the scale from Kelvin to degree Celsius, and then sorting the dataset into a lon according to their longitude. So I am running this code. It will take a bit of time because I have given a lot of code to run in this one cell. Next, we are again plotting. Next, this time let's plot a historical file. So I'll just change this DS historical and then task and select a date before 2014. So maybe 2005. And you can also see which line it is running now. See this green small arrow. So this much is done, and this is now running this line of code. And yeah, soon it will be done, I guess. Yeah. But again, this will take time, because it is subtracting all the values. Like it's subtracting to 73.15 from all the values. Okay, so it is done. So I changed the bottom code. So let's now look at how it was in historical day. Yeah, so it looks like this. The temperature doesn't have a unit here because I already changed it to Kelvin. So it is not showing the, sorry, degree Celsius. It is not showing the previous thing. Now, again, the locations are Santiago and Boston. We can change the location right now. Maybe instead of Boston, let's look at Cordova. So I'll just take the name of Cordova here and paste it here instead of Boston. Yeah, let's look at this two now. So I'm getting the latitude and longitudinal values of these two locations, then getting the nearest values from the file, and that's how I'm getting the historical values from location 1 and location 2 for both um, historical and future data, right? Next, we are calculating a warm spell duration index. Now, this is an index value. We are not going to use extreme value distribution here. Now, what this index do is how many days a warm spell stays. So what is this? Like in climate study, this approach is used to define what counts as an extreme or unusual relative to a historical reference period. So the WSDI is actually a sequence of at least 6 days where a certain threshold is exceeded. So certain threshold we have calculated from a baseline period. The baseline period is 1961 to 1990, and find out the 90th percentile values. So what is the value that happened only 10% of time in this baseline, and we got the threshold from that. And if that threshold is exceeded for consecutively 6 days, then it we can say that it's a like we can calculate the WSDI or warm spell index, right? So this is what we will be doing. So this is the duration index. This is the code to calculate this one, and then we are plotting. Let's plot these two. Oops, it is still showing Boston. Maybe in somewhere I have kept the name Boston here. Let me see if I can find. Yeah. So see the location is Santiago and Boston. We have to change it to Cordova. I'll give you the changed file, so no worries. It is running again. Yeah, so this now we have Santiago and Cordoba. So let's see what it is saying. So for location 1, historically it was 11.29 days per year where the warm spell was seen. So at least 6 consecutive days and then more than that. So we saw that 11.29 days, but future there will be 94.79 days per year above the threshold. So and also it is showing the threshold for these locations. So for location 1, which is Santiago, for us the threshold is 19.42 degrees Celsius, and for Cordova the location threshold is 25.82. In location 1, the absolute change would be 83.5 days per year, and percentage is 739.53%. For location 2, which is Cordoba, historically there were 9.8 days per year. In future, it will be 50.95 days per year. Absolute change is lower, percentage is also lower. But you can see in the more colder areas, I would say in Santiago, where the location, like threshold temperature was 19.42 degrees Celsius, the impact is higher, right? So that's what we can see here, the change in 83.5 days. Okay, so this is that. We can also calculate nighttime maxima. So, what is the maximum night temperature that we can consider as a index here? Because usually the temperature is higher at daytime and then at night it gets lower, so that we all get some time to cool down. All the living human beings and everything, all the infrastructure also they get heated as well. But if the temperature at night is also high, then that means there is a heat stress going on and something like that. So I have selected a very basic nighttime maxima equations to show you the extreme value distribution of that. And if we plot this line, we again get a return level of nighttime maxima. I think I have selected Santiago again and maybe Boston or Cordova, I don't remember. But let's see what happens here. Yeah, so it is yeah, so it is doing now for Santiago and Cordoba. So nearest grid point it found is this one for Santiago and this one is for Cordoba. And now we have return levels in degrees Celsius. So you can see Santiago historical 30-year nighttime maximum is 26.78 degrees Celsius. So 30-year return level is 26.78. In future, it will change to 34. There will be a change of plus 7 degrees. So in future, nighttime maximum would be 34. That is quite high. If you think of in degree Fahrenheit, it is, I think, around 100. Um, yeah, just check that. But currently in Santiago, 100-year values are 27.66 and 35.40. In Cordova, it's even more. Currently, 30 years are 36.03 and 44.37 in future. The nighttime maxima might be. So, yeah, you can look at that and do different analysis. You can change the location to any of these. So, you just add new locations here. You add the names, maybe New York, and then do the latitude and longitude of New York. I'll just copy this one, put a comma after. So latitude is 4.71 and longitude is 74.00. Sorry, 40.71. This is a positive, and longitude is 74.00. Yep. So like you can keep adding new locations here and you can find out for different location what is the extreme value for precipitations, what is the nighttime maxima, or what is the warm spell duration index, all of that using this code. We can use different models if we have them downloaded in some location in our drive. We can use different time periods, different ssps. So like a lot of things can be changed here, and we can do we can find information about this. So hopefully you could run all of these. There was no problem, but we will soon have a Q&A session, and you can ask me questions there about if you had any difficulties running these codes, or if you have any difficulties learning about the art system models, or anything about how they are generated, how they're stored, everything. Yeah. So see you in the Q&A sessions.